Alright, let's determine an equation in the form of f of x is equal to ax plus b over cx plus d for a function that has asymptotes with an equation x is equal to -2, y is equal to 1, and a y-intercept of 2. Okay, so in this case, we can understand that because they gave us a template, the degree of the numerator and denominator should be 1, right? So because the degree of the numerator and denominator should be 1, then because they have the same degree, we know that the horizontal asymptote occurs y is equal to a over c, right? Excuse me. So, having said that, we know that the vertical asymptote is x is equal to -2. And we also have a point 0 and 2 for the y-intercept. Okay, so let's kind of piece this function together. So we know that the vertical asymptote is going to have x plus 2 as a factor, right? And we know that the horizontal asymptote here is going to be +1, right, from what they've given us. So for the numerator, let's say that we have x, okay? And we also have a y-intercept of 0, right? So if there's a y-intercept of 0, we know that y-intercept of 2, we know that f of 0 should be equal to 2, right? So what we could do here is I'm going to add +4, right? And the reason I'm adding +4 is if you look at f of 0, you get 0 plus 4 over 0 plus 2, and you actually get 2, so you get 0 and 2, right? So you need to make sure that that also will work out, and this could be our potential function. So you can actually have different answers for this, right? But basically this could be our potential function where f of x is equal to x plus 4 over x plus 2. Now we still have to sketch the function. So to sketch the function, I'll look at a few things. We know our vertical asymptote, we know our horizontal asymptote, we know that one of the points, the y-intercept is 0 and 2. I'm also going to find my x-intercept. So if I find my x-intercept, I'm going to let f of x equals 0. So all you have to do, we know that if a rational function is equal to 0, the numerator is equal to 0. So x plus 4 is equal to 0, x is equal to -4. So your x-intercept is -4 and 0. I'm just going to sketch this down here. I think all of these points should suffice. Okay, and we can understand that our vertical asymptote is -2, so I'm just going to let each of these squares represent one unit. So this is your vertical asymptote, x is equal to -2. Horizontal asymptote is 1, so I'm just going to do that. And let's use a different color, let's use gold. Okay, so the horizontal asymptote is 1, so y is equal to 1. Okay, and we also have an x-intercept, 0, we have a y-intercept 0 and 2, so let's say that's right here. We also have an x-intercept at -4 and 0, so let's say that's somewhere here. So I'm just gonna, oh, sorry about that. So this is where the axis is, so it's like here. Okay, so this is 0, this is -4 and 0. Okay, and let's construct our trace here. So we just have to follow the confines of our asymptote, so you can use some test points here to do that more effectively, right? So you can kind of see that there, and also we'll have another point here. Whoops. Okay, and I'll follow the asymptotes. So you can notice here that as x approaches -infinity, right, as we're going this way on the trace all the way to -infinity, y actually approaches the horizontal asymptote at 1, but from below the horizontal asymptote. So I'm going to write this as 1 negative. As x approaches the vertical asymptote, which is -2, let's say from the left side, so -2 negative, y actually approaches, you can see if you follow the trace, it goes all the way to -infinity, right? So if we approach the vertical asymptote from the right side, to -2 from the right side, you can see that y, if you follow the trace, it actually will approach +infinity. right? And for the last case, if we're looking at end behaviors, as x approaches positive infinity, you can actually see that y approaches the horizontal asymptote from above, y approaches 1 from above. Okay, so this is a really interesting way to kind of just gauge the behavior of our rational function. So this is basically the sketch of a rational function. Alright, let's write an equation for a rational function whose graph has all of the indicated features: a horizontal asymptote with an equation of y is equal to 5, a vertical asymptote with an equation of x is equal to 4, and a hole at x is equal to 1. Okay, so we know that a rational function, let's say r of x is a rational function, it's going to have a function on the numerator, f of x, and a function on the denominator, g of x. Now, a hole will occur, right, when the rational function is equal to 0 over 0, and that's going to occur when you have the same factor. So we know that the hole occurs at x is equal to 1, so your rational function should have x minus 1 on your numerator and x minus 1 on your denominator. Okay, so that way if you do plug in 1 here, you get 0 over 0, and this indicates, and this creates an indeterminate state, and this is one of the hallmark features of a hole, right? Now the other point that we need to do here is there is a vertical asymptote of x is equal to 4. So I'm going to write down x minus 4 on the denominator, and now if you plug in 4 here, you're going to get some kind of constant over 0, and this is the hallmark feature of a vertical asymptote, right? And the vertical asymptote VA occurs when x is equal to 4. Okay, so we have an x minus 4 on the denominator, and for the last step, we have a horizontal asymptote with an equation of y is equal to 5. But we know that these two are going to cancel out, so we need to put some kind of factor here that will create a horizontal asymptote of y is equal to 5. We understand that if you have a function that looks like axn plus c over bxn plus d, where the factor or the expression on the numerator and the expression on the denominator have the same degree, then the horizontal asymptote occurs where you have the coefficients a divided by b, right? So in this sense, I'm going to put down any kind of coefficient on any kind of expression with a power of 1, so a linear expression, 5x, with a coefficient of 5, because 5 divided by 1 will give us the horizontal asymptote, and I'm just going to put any number, right? So collectively, the function r of x is equal to x minus 1 times 5x minus 3 over x minus 1 times x minus 4 will basically meet all of these criteria. And you can obviously have different solutions to this, right? This isn't just the only answer. Your answers can vary, but for the most part, this is just a really quick way of meeting all of these criteria. Alright, let's use the asymptotes and intercepts to make a quick sketch of the function f of x is equal to x minus 2 divided by x plus 4, and describe the symmetry in the graph if there is any, and also determine the intervals of increase and decrease for f. Okay, so let's take a look at our function f of x is equal to x minus 2 over x plus 4. I'm just going to write down the domain and the range first. The domain here, x belongs to all real numbers, x cannot equal negative 4, right? Because then the denominator would have a restriction. This is a plus 4, by the way, right? I'm just going to rewrite that. Okay, and when you have a restriction on the domain, this implies a vertical asymptote, so the vertical asymptote occurs at negative 4. Okay, so vertical asymptotes are the restriction on the domain. The range here, y belongs to all real numbers, y cannot equal, and because our function is a rational function and it's in the form of axn plus c over bxn plus d, and the degree of the expression on the numerator and the degree of the expression on the denominator are the same, then the horizontal asymptote, let's write HA here, the horizontal asymptote occurs when y is equal to a over b. So this only occurs, you can use this equation when the degree of the numerator and denominator for the expressions are the same, right? So in this case, a over b here is basically there's 1 over 1, right? So y cannot equal 1. So this is your restriction on your range. Your horizontal asymptote is your restriction on your range, and we know that y cannot equal 1. right? Now to help us out with our sketch, what we're going to do here is we're going to also find intercepts. So I'm going to find the x-intercept. The x-intercept, I'm going to let f of x equals 0. We know that if you want to make a fraction 0, the numerator has to be equal to 0. So all I have to do is equate x minus 2, the factor of the numerator, to 0. X is equal to 2, so our x-intercept is 2 and 0. Okay, now to find our y-intercept, right, we know that the y-intercept is where the graph hits the y-axis. I'm going to let x equal 0. So you're basically doing f of 0, which is 0 minus 2 over 0 plus 4, which is negative 1/2, right? So the point here is 0 and negative 1/2. And now we have our x-intercept or y-intercept. We also have the vertical asymptote and we have the horizontal asymptote. Okay, and now what we're going to do here is we're going to create a sketch, right? So if we're creating a sketch, I'm just going to do that here. Right, so if we're creating a sketch here, I'm going to first plot my x and y intercepts together. I'm going to first plot my vertical and horizontal asymptotes. Right, so I'm going to do the vertical asymptote in red, so x is equal to negative 4. You can use the grid here. Alright, so I'll just do it here. Say this is x is equal to negative 4. And y is equal to positive 1. Let's do that in orange. So this is the horizontal asymptote. Y is equal to 1. Right, and we also have our intercepts. So our intercepts are 2 and 0. So let's say that's here. And negative 0 and negative 1/2. So it should be like, let's say it's like here. This is 0 and negative 1/2. This is just a sketch, by the way. So this is 2 and 0. Right, don't consider this point. And we just follow the confines of our asymptotes. So we know that asymptotes are points of the graph where the graph won't touch but will approach infinity, right? So we can assume here that as we approach the asymptote, as x approaches negative 4 from the right side of the asymptote, y actually will approach infinity. In this case, y approaches negative infinity, right? And I'm going to do the same thing here using the confines of the asymptote. And you can use some test points to actually create an appropriate graph, right? So I'm just going to, but you can see that it'll just basically keep going until it approaches the asymptote, right? And as we approach the asymptote negative 4 from the left side, y will actually approach positive infinity. Okay. Furthermore, as x approaches positive infinity, so as we're going this way, we can see that y actually approaches the horizontal asymptote 1, and it's actually approaching from below. And as x approaches negative infinity as we go this way, y is approaching the horizontal asymptote from above, right? So you can see that with the trace, right? So this is our sketch. And we also want to determine intervals of increase and decrease. So I'm just going to do that here. So an interval of increase, where you'll see basically a positive secant, or positive tangent if you keep drawing it to each point. You can see that there's an interval of increase from negative infinity to the negative 4 mark, right? This would not be inclusive, so x belongs to negative infinity to negative 4. We also have an interval of increase from this end to this end, right? If you draw a secant, it's just this one is an exponential increase. This is more of a progressive increase. The rate of change actually diminishes over time. So union negative 4 and positive infinity. Okay, so both of these intervals are intervals of increase. There are no intervals of decrease here, so not applicable. Okay, if we want to describe symmetry, we can also do the test. I want to test to see if this is actually an odd function. We know this wouldn't be an even function because there is no line of symmetry along the y-axis. So what I'm going to do here is I'm going to do f of negative x. If this is equal to negative f of x, this implies that we have an odd function. Okay, so if I do f of negative x, I get negative x minus 2, negative x plus 4. If I simplify this, this is basically negative x minus 2 over negative x plus 4. If I factor this out, we get x plus 2 over negative x minus 4 cancels out, right? And you can actually notice here that this isn't an odd function, right? Because negative f of x, which I'll just do out here, let's say we can just kind of erase this portion. Right, like negative f of x is basically negative x minus 2 over x plus 4, which is basically x plus 2 over x plus 4, not x minus 4. Right, so you can see that this is not an odd function, and the reason it's not an odd function is because f of negative x does not equal f of negative f of x. Okay, so it's not an odd function, but we did look at the intervals of increase and decrease. Okay, so that's the idea.